The model described in the first part of this lecture uses a two-dimensional finite difference approach, and it is that which I now want to describe in more detail. Essentially, it is based on breaking the sample into small cells and calculating the temperatures of the nodes or the corners of those cells. So here I've labelled a set of nodes with two indices, M and N, essentially, showing where the node is in two dimensions. And what I'm going to need to do is to be able to express the differential equations in terms of these nodal temperatures, and then to solve for those nodal temperatures to get the results that I need. You'll note that in the y direction the mesh spacing is delta y, in the x direction it's delta x, although if you look at this diagram, delta x and delta y basically look the same, and later on I will assume that delta x and delta y are indeed the same, although they do not have to be in the general case. So the first thing I need to do is to get a finite difference version of the differentials, and I can do this quite easily if I can consider the formal definition of differentiation, which I've done here for partial dt by dx, that we would get by taking the limit as delta x tends to 0 of the temperature x plus delta x minus the temperature x divided by delta x. And essentially all that we're doing in the numerical method is letting delta x remain finite, so that our differential is approximated by the temperature x plus delta x minus the temperature x divided by delta x. So in terms of the mesh I've already shown, that means partial dt by dx equals 1 over delta x, temperature T m plus 1n minus the temperature at Tmn. So temperature at this node minus the temperature at this node divided by delta x. But that just gives me my first order differential. In the generalized heat conduction equation, I of course have a second order differential. So what I'm showing here is that the second order differential of t with respect to x will equal 1 over x times the first order differential of t with respect to x, evaluated at x plus delta x, minus the first order differential of t with respect to x, evaluated at x. And then I've simply rewritten that in terms of the nodes shown here. So in the first case, for x plus delta x, I'm looking at the temperature difference between this node and this node. And then for the second case, I'm looking at the temperature difference between this one and this one. And then I've simply rearranged the equation slightly to give my overall result, that partial d2t by partial dx squared equals 1 over delta x squared, the temperature of t of the node m plus 1n minus the temperature of node mn, but 2 times that, plus the temperature of the node m minus 1n. I have a very similar result for the second order differential with respect to y, except now the adjacent nodes that you consider are the ones in this vertical direction, so that overall my second order differential with respect to y is 1 over delta y squared, temperature of the node m n plus 1 minus 2 times the temperature of the node mn plus the temperature of the node m n minus 1. And if I now consider a steady state situation, so there is no time variation, I will come on to consider the more general case of time variation in the next session, then my two-dimensional steady state heat transfer equation will simply be the second order differential temperature with respect to x for the second order differential t with respect to y, plus my internal heat generation term, which is q dot over k, and the total of this lot will be 0. So all I've done at the bottom of this slide is substitute in my expressions for those two differentials in terms of finite differences. I'm now going to make the simplification that I do have a square grid so that delta x equals delta y. This allows me to simplify the equation a bit, and I've also rearranged it slightly so that the only term now that involves a distance is the q dot over k term, and is multiplied by delta x squared. This means that if q dot equals 0, I have a simple equation that relates the temperature of a given node, mn, to the temperatures of the 4 surrounding nodes, m plus 1n, m minus 1n, m n plus 1, and m n minus 1. And the sum of those temperatures minus 4 times the temperature of the node Mn equals 0.